带走黑夜，青草的露水，大家一起来称赞生活多么美。我的生活和希望总是相违背，我和你是河两岸，永隔一江水。波浪追逐波浪，海呀一对对，姑娘人人有伙伴，谁和我相配？等待，等待，再等待，心儿已跟随。我和你是河两岸，永隔一江水。波浪追逐波浪，海呀一对对，姑娘人人有伙伴，谁和我相配
？Hello. Hello, can you hear me, guys? Can you see my screen? If you can, yeah, you can type yes. Okay, great. Thank you, Marco. All right. Okay, so we have 5 students here. Maybe we can wait for 1 more minute for another one. I'm not sure how many. Well, everyone can attend this class, but let's wait for 1 more minute. Okay, let's get started. So tomorrow, today is the 3rd lesson of this artificial intelligence and machine learning course. So today we're going to introduce a very interesting, very important thing, which is the neural networks. Okay, so what we're going to cover today we're going to introduce what is a neuron in computer sense, not in biological sense. Okay, what is a neural network? And we're going to introduce something like an input, weight, bias, net input, whatever, some concepts. Okay, so they are very straightforward. It's not really complicated. But we're going to talk about several other things. It's called the activation functions, which means whenever a neuron receives a message, the reaction, how it's going to react, what is the strength of its reaction. So we call it the activation function. Okay, so there was 2 activation functions. One is called a sigmoid and the ReLU. So we're going to see that. It's very, very straightforward, but the name looks like, some other, yeah, the name looks like a strange, right? But we're going to get used to it. And the cost and the loss. Well, cost and the loss, they are the same thing. Here is the same. What is the loss? The loss is we use machine learning. Here we talk about neural networks, right? Neural network is a kind of is a model. We can use it for machine learning, right? So in this machine learning technique, so how good it is, how many mistakes it makes, right? So the mistakes means the loss or the cost. So yeah, so we're gonna see that. And finally, we're gonna do a project. Today, we're gonna do some like a very interesting thing and a very important technique. It's called a face mesh. The face mesh is a neural network model created by Google. And it is very useful. Why it is useful? I'm going to show you a project which just based on this face mesh project. The project we're going to do as a homework today, and it won the 3rd grand prize at the International Science and Engineering Fair, which is a very grand, it's a very prestigious prize. Yeah. Okay. So, well, guess what? When I look at the material for you guys to use, well, it took me like it took me some time, more than I thought. Why? Because it is not easy to find the material, the teaching material, just for you guys. Okay, it's easy to rigid, which means for college, right? Or it is just like a very basic concepts for like a very average students. So, but what is the best material? I look around. Actually, I found a very good one, but it is really good. It is not really easy, but it is appropriate for you guys. Okay. Yeah, where it is here. It is Intel. You know Intel. The Intel is the company make those CPU, which a lot of PC gonna use, right? PCs will use. So this is Intel deep learning training material. So we're not gonna cover all of them, but we're gonna cover 70% of them, which means we're pretty rigid as well. Yeah, but not as much as the professionals, right? Because this material is for professionals. It's actually okay. Let's open the material. Let me see. Okay, great. So here it is. So what is a neural network? Essentially, neural network is a machine learning model. Okay, so we've been heard about it so many times, I believe, right? So it is essentially the deep learning. When we talk about the deep learning is all about neural networks. Okay, so neural networks is really, really important. If not all, most of the very innovative projects, I mean, AI stuff is created by neural networks. Okay, so, all right, so what is the motivation of neural nets? Neural nets is essentially, it's an analogy to biology, right? The biological stuff. What is that? Use biology as inspiration for mathematical model. Of course, neural networks is basically, it's a mathematical model, okay? But we got some inspirations, we got some ideas from the biological stuff, right? Well, essentially the brain, how our brain can work, okay? Well, essentially what we say is each neuron gonna get some signals, receive some signals from other neurons. That's number one. This is the first assumption. Number two is it's going to generate some signals, which means the output or the response, right? It's going to create some response to the input signal, okay? And when a neuron create a signal, it's going to pass to some other neurons, right? Other neurons, which means for a single neuron, it's going to pass its signals to many neurons, not only one. Okay, so this is some inspiration from biology. Okay, so this can be a fairly complex model, right? Complex model, because each neuron going to receive signals from others, and it's going to pass the signal. I mean, its response to many other things. Okay, so how it's going to work? So essentially, what this says is we're going to assume one thing. We assume the neurons going to be in different layers. If you look at here, you're going to see, hey, this is a layer. We call it the input layer. Okay. And we got an output layer, right? Yeah. And in between, there is some other layers. Each layer receives signals from its previous layer, and it's going to send the layer to the next layer, send signals to the next layer. Okay. So all these are assumptions. Okay. Is this right or wrong? Whether this is, it is not related to how the brain actually works. It's just get some inspirations, get some ideas. We borrow some ideas from the biology to create such a mathematical model. That's what we call it a neural network. Okay. All right. So it's actually just like this. It's not that complicated. Let's take a look. Let's take a closer look. Look at here. So this is the input, right? So whatever the external signal going to input to our body, to our brain, right? So we're going to say, hey, there is an input. And also can think of as a complicated computation engine. Okay, we think these is an engine. Well, this engine is a black box. Well, it's going to be fairly complicated inside. And we can train it using the training data, which means we can input, let's say each time the input can be an image, right? Can be an image, a picture. Okay, we input one picture, it's going to have an output. And we input another picture, it's going to have an output. We input the third one, fourth one, many of the pictures. Just like our eye, we can watch many pictures, and it gradually we identify what is the cat, what is the dog, who is who, what is house, right? What is the vehicle. So we essentially input is the data we collect from the world for us to learn, right? Okay, and then we can train it. Which means this whole thing can learn. Yeah, given the more data we give to the input to the neural net, to the network, the better it will behave in prediction, right? So it's going to be better and better, just like a student. He can learn, and the student is going to be like more and more educated, right? And then hopefully it will give good answer to new data, which means eventually this engine is trained, like we mentioned in last two classes, right? And it can predict, which means I just receive an image. This thing can give you the answer, can tell you what it is, right? So this is the neural network, okay? Yeah. The next one, let's take a look at just a single one, a single neuron. Okay, let's zoom. Let's just zoom into anyone, okay, any one of them, okay. So what's going to happen with a one? Well, what we see is essentially we're going to have some input from previous layer, okay, the previous layer, right? It's just we said, okay. The second thing is, well, the input could be more than one, could be many inputs, but there will be holistic effect to this neuron, which means let's say this way, you guys, where there are three guys, you guys push me, right? Some are going to push it very hard, some are you push like not really hard, but no matter what, my body going to feel a holistic effect, right? Just saying, yeah, I got something, right? I got some force as a whole, right? So that means, yeah, it's gonna. So all these input, we have to have some way to calculate the effect, the holistic effect, right? Effect, right? So that is what we says. Okay, and also we have something. It's called activation function, which means what I received, the signal I received is not the strength I output, which means maybe you push me very hard, but I don't move. So the externally, you don't feel, I just behavior not in the proportion to what you guys push me, okay? So this, it's called a activation function, which means how strong the holistic signal I received, and what is the response I output. Okay, there is a function. It is not the same, but they have some relations. Okay, there is a function. So this is what it says. We got some input. There is a holistic effect, right? Yeah, we're gonna use some like a very simple mathematics to express it. You're gonna see that. Yeah, just add them together. Yes, almost just like that. Add them together. That's the holistic effect. And there is it's like an activation function, which means how I respond. Okay, I'm probably going to be like a resistant. Maybe I can promote this signal or whatever. There is a function, right? There is a function. And then with that function, I'm going to output a signal to others. Okay, I'm going to output this neuron, going to generate an output. That output will be the input of other neurons in the next layer, right? Okay, so this is what it says. The neuron output the transformed data, right? How to transform using this activation function. It's a function. Yeah, it's a function. Yeah. Okay, so let's take an example. Let's take a look. Okay, let's go to some mathematics now. Okay. Yeah, let's say we have an input, which is X. Okay, we have an X, the input, whatever it is, just give a number, any number. The X1 could be any number, let's say 0.5 or something, 0.7, I don't know. Yeah, this is an X. This is the input of another one. This is the input of another signal. So we have three signals, three input. However, there is a weight, which means some of them has a strong effect. Some of them may have like a lighter, effect. So we're gonna put some weight. Okay, we can put the weight. So our formula could be X1 times W1, X2 times W2, X3 times W3, which means the effect on this neuron actively, right? Yeah. Okay. So how can we know the sum? The whole thing, the holistic thing. Add them together. We can add all these together. That's it. Okay. Maybe there is something just related to this neuron. So which means there is a bias. It's called a bias. Okay. There is a bias over here. So what we're gonna do is we're gonna add the input times weighted for the first signal and the second weighted signal, right? Third weighted signal, add them together and add the bias. The bias is just inherent to this neuron, okay? It's a number, okay? So mathematically, what we can do, we can create a simple, right? Simple mathematics formula. Yeah, simple formula. This is the formula. What is the formula? It's right over here. Just add them together, including the bias. The bias is nothing to do with the external input. It's just something about this neuron, okay? If you say there is no bias, then the B is 0, right? Let's assume it is not 0. It may not be 0, okay? So that's it. So this is the holistic effect of all these input and external, internal effect. I mean, the holistic effect, including the external inputs and internal bias. This is an internal bias. Okay, so then we got this simple formula. Okay, well, can you believe that? This is all about neural networks. The neural networks is as this easy. Okay, it's probably less complicated than you thought. Is that right? Okay, one more step. As we said, this is the holistic effect. We have a activation function, which is F. This F is a function. Z is the holistic effect. So that means, well, this is the whole thing. However, my output, the behavior, right? My response could be a little bit differently. However, I do have a formula, the F. F is a function. Okay, F is a function. How F looks like, I show you. Okay, so up to now, what do you think about neural networks? You think it very hard? That's it. This is everything. Yeah, this is everything about neural networks. This is how it's built. Okay, so let's summarize it. The net input will be the Z, it will be the bias plus the, the signal multiplied by the weight, right? And put them together, summarize. I'm not sure if you know, can you guys tell me whether you know this sigma? This sigma, you know that, right? Okay. Okay, I heard something, yes. No. Okay, great. This is about that formula. And also, what is the B is the bias, what this says, and F is the function, is the, activation function. And A is the output, which means this is the response. This A is the input of the neurons in the next layer. Okay, so with this mathematics, which is it's not complicated, and we build our neural networks, and this neural networks used by all these scientists and engineers or business, that's it. And what? It is most, innovative. It creates so many innovative technologies, okay. Right. Any questions? Okay, now let's put them together. Let's take a look at another thing. Okay, what is it when I talk about the function, right? The activation function. This is the activation function we're going to use. This is the often used, frequently used activation function. What is this? What this says? What this says is if the holistic effect is negative, very large negative, the output is going to be 0. Look at here. This is this is output, right? This is input. Okay. Oh, yeah, I'm not good in writing. What this says is, look at here, this is 0.5, okay? If I feel nothing, okay, if the neuron feel nothing, I'm gonna output 0.5. If I feel like a very negative signal, okay, negative signal, I will output nothing, 0. If I feel like a very strong positive signal, extremely strong, the output is 1. Look at here, this is 1. This is 1. Okay, so this is usually, usually a cell, an actual cell, right? It's a biological cell kind of behavior. If you, let's say your ear, right? Your ear. If you input a very, very loud, extremely loud signal, how it's going to behave? It's going to behave a maximum, which is still a limited signal, right? So that's what it says. That's what it says. Okay, so this is what we call it the sigmoid function, which is frequently being used in the neural network as a activation function. Okay, this activation function is very interesting. This activation function is basically solved a very important problem, because if we use, as we know, all the formula, I'm sure this is beyond your knowledge, but a very interesting thing is I can tell you just the conclusion, right? If you look at here, all these are linear formulas. So all the linear formula, if we superpose them, just put them together, that's still a linear system. However, our biological system is a nonlinear system. How can I mimic it? How can we simulate it? We just use this activation function to realize that from linear to nonlinear, from linear to linear. It's so important because that is the way we can simulate the real world. Okay. All right. So that's the activation function. This is the sigmoid. This is some mathematics. We don't want to do that. Never mind. We don't do that. The derivative. We don't want to do that. Okay. Derivation. We don't want to derive those kind of things. But yeah, let's assume this is true. Okay. Just give you a real example. If you say, hey, this is a formula, we just, this is a formula, input, weight, right? Input, weight, and the bias. And we assume the activation function is sigmoid. What is the output? What is the A, right? A is equal to F of Z, right? How can we do that? Let's just do some mathematics. Okay, I'm not gonna, I know you guys are good in math. Yeah, let's assume this is like a input 1 is 0.9 and the weight is 2, and this is 0.2, weight is 3, input is 0.3, and this is the weight is negative 1, and the bias is 0.5. Let's do, and in between, this is the activation function is the sigmoid. Let's just do some mathematics. Okay, I'm not going to do that. I trust it. Okay, so now essentially, finally, the output will be 0.93. That's it. So this is the mathematics. This is all the mathematics about one neuron in mathematics, in the neural networks. Okay, so it's probably less complicated than you thought, right? That's it. Okay, so the neuron would output a value 0.93. Yeah, that's it. Right. Okay, so this is now this slide is going to answer some general question. Why not just use one single neuron? Why do we need a lot? Why should we need a larger network? Why just we use the single one? Well, it explains, just like I just mentioned, a single neuron only permit a linear decision boundary, which is not sufficient because our real world is non-linear. So let's say this way, yeah, you wanna mathematics to do non-linear stuff, but your model can only handle linear. How can you handle that? There is no way. So that's why most real world problems are considerably complicated. So we need this complicated neural network. Okay, that's essentially, I mean, yeah. Okay, so this is the network. Okay, if we, again, let's put them together, right? Previously, we just investigate just one neuron. Let's see, how can we put them together? We put them together, we call it what? Feed-forward neural network. Why? Because the propagation is from the left to the right, from the input to output. Okay, does that make sense? Yes, absolutely. Everything is, we get an input, we're gonna process it, and output. This is the biological system, right? All right, so it makes sense to us. Okay, so this is the feed-forward neural network. Okay, so as we said, there is many weights. Why? Because each layer, let's say each layer, each input layer and the output layer, between the input layer and the output layer, every pair, every possibility connection, right? They have a weight. Let's say, from here, this, we have three neurons. The actual neuron is much more than three, right? Just for some like, visual, just for our teaching material, we just list the three of them. This, we have four. So how many connections are there? Can somebody tell me? All these green connections, how many of them? We have three here, four here. My question is, how many green lines in between? Okay, just type it. Let me see who can type it. Give it a number. Wonderful, Kevin. Wonderful. 12, right? 12 connections. Well, you can imagine, what if this is a 300? What if this is a 400? That will be a fairly large number. Okay, the actual might be even larger than this, right? In our biological system. So the connection is very big. Yeah, the connection is very big. You can imagine that. So the computation is very intensive. That's what I want to say. Yeah, even a single neural will apply very simple mathematics, just we mentioned. However, the holistic computation is huge, right? Because we use neural networks. Okay, so the weight is something in between, right? There's many weights. Okay, nice. The next one, what I want to say is, the first layer, we call it the input layer. Okay, the layers in between input and output, we call it hidden layers. Look at here, hidden layers, right? Hidden layers. We just give them a name because we can see that, we can feel it because it's an input, and output can feel it because it's gonna output, just tell us, right? But what's in between, we don't know, it's hidden. Yeah, it's hidden, okay. And there is the output layer, well, because yeah, there is output, okay. So this is the whole thing, this whole thing is a neural network. Okay, this whole thing is a neural network. Okay, there is a couple of more stuff. This is more like some like notations. It's not really important for me. However, this is the very last one. We almost finished the Intel training material. This is the training material for Intel engineers. They are professional engineers. You guys should be proud of yourself because if you can follow this. Okay, so now we know the feed-forward neural network do computation. Yes, we know it does computation. Yeah. Next, we will learn how to adjust with the neural. Okay, so this is the feed-forward. You probably have a question. Okay, so how do we know? How do we know these these input and weights, how do we know that, right? How do we know that? Because initially, how can we set it? Well, if it is training well, it is already trained. All these numbers are fixed. But originally, how can we know that one? Okay, so that comes from training, right? The training. Initially, we don't know. You can randomly set some numbers over there. But eventually we can train it. We train it, and eventually it got learned, and it can, set up a right model that can help us to do something, right? Like, for example, image classification, as we did. Okay, so what this want to say is the very last one, the very last page. What it says is, we will learn how to adjust the weight to learn from data. So learn from the data means the training, right? Well, let me just tell you, this we're going to cover the next time, the next class. Okay, we're going to cover how to learn. Okay, so now today we just introduce what is a neural network, how it works. Okay, and how to train it. That's another topic we're going to cover next time. Well, essentially, as this says, we're going to adjust the weight, a well-trained model will give you the right weights. Okay, so we're going to train that. And also, I can give you a heads up that there is a rule. It's called the chain rule. It's called a chain, CHAIN, chain rule. What does that mean? Is so to adjust the weight, we come from the output and back. It's a backwards process. So we're gonna start from the output, and then the very last hidden layer and the second last hidden layer all the way to input. That is the direction we want to adjust the weight. That's the training process. Okay, we're going to cover that next time. Okay, so really good. However, before, let me see what I have for you. I have some good stuff for you. All right, so we have already covered this one. Okay, so we finished. Now I have a video. It's a really good video. I really want you guys. It's gonna take like 15 minutes maybe or so. It's not very long. I want you guys to watch this. It will give you a very good explanation with some animations. Okay, it's kind of a live. Rather than I can show you some slides. It's pretty like a static, but this one is dynamic. Very good. Okay, let's take a look. Okay, let me click on that. Okay, by the way, can you hear that sound? If you can type yes or no.
This is a 3. It's sloppily written and rendered at an extremely low resolution of 28 by 28 pixels, but your brain has no trouble recognizing it as a 3. And I want you to take a moment to appreciate how crazy it is that brains can do this so effortlessly. I mean, this, and this are also recognizable as 3s, even though the specific values of each pixel is very different from one image to the next. The particular light-sensitive cells in your eye that are firing when you see this 3 are very different from the ones firing when you see this 3. But something in that crazy smart visual cortex of yours resolves these as representing the same idea, while at the same time recognizing other images as their own distinct ideas. But if I told you, hey, sit down and write for me a program that takes in a grid of 28 by 28 pixels like this, and outputs a single number between 0 and 10, telling you what it thinks the digit is, well, the task goes from comically trivial to dauntingly difficult. Unless you've been living under a rock, I think I hardly need to motivate the relevance and importance of machine learning and neural networks to the present and to the future. But what I want to do here is show you what a neural network actually is, assuming no background, and to help visualize what it's doing. not as a buzzword, but as a piece of math. My hope is just that you come away feeling like the structure itself is motivated, and to feel like you know what it means when you read or you hear about a neural network quote-unquote learning. This video is just going to be devoted to the structure component of that, and the following one is going to tackle learning. What we're going to do is put together a neural network that can learn to recognize handwritten digits. This is a somewhat classic example for introducing the topic, and I'm happy to stick with the status quo here, because at the end of the two videos, I want to point you to a couple good resources where you can learn more, and where you can download the code that does this and play with it on your own computer. There are many variants of neural networks, and in recent years there's been sort of a boom in research towards these variants, but in these two introductory videos, you and I are just going to look at the simplest plain vanilla form with no added frills. This is kind of a necessary prerequisite for understanding any of the more powerful modern variants, and trust me, it still has plenty of complexity for us to wrap our minds around. But even in this simplest form, it can learn to recognize handwritten digits, which is a pretty cool thing for a computer to be able to do. And at the same time, you'll see how it does fall short of a couple hopes that we might have for it. As the name suggests, neural networks are inspired by the brain. But let's break that down. What are the neurons, and in what sense are they linked together? Right now, when I say neuron, all I want you to think about is a thing that holds a number, specifically a number between 0 and 1. It's really not more than that. For example, the network starts with a bunch of neurons corresponding to each of the 28 times 28 pixels of the input image, which is 784 neurons in total. Each one of these holds a number that represents the grayscale value of the corresponding pixel, ranging from 0 for black pixels up to 1 for white pixels. This number inside the neuron is called its activation. And the image you might have in mind here is that each neuron is lit up when its activation is a high number. So all of these 784 neurons make up the first layer of our network. Now jumping over to the last layer, this has 10 neurons, each representing one of the digits. The activation in these neurons, again some number that's between 0 and 1, represents how much the system thinks that a given image corresponds with a given digit. There's also a couple layers in between, called the hidden layers, which for the time being should just be a giant question mark for how on earth this process of recognizing digits is going to be handled. In this network, I chose 2 hidden layers, each one with 16 neurons, and admittedly, that's kind of an arbitrary choice. To be honest, I chose 2 layers based on how I want to motivate the structure in just a moment. And 16? Well, that was just a nice number to fit on the screen. In practice, there is a lot of room for experiment with a specific structure here. The way the network operates, activations in one layer determine the activations of the next layer. And of course, the heart of the network, as an information processing mechanism, comes down to exactly how those activations from one layer bring about activations in the next layer. It's meant to be loosely analogous to how in biological networks of neurons, some groups of neurons firing cause certain others to fire. Now the network I'm showing here has already been trained to recognize digits, and let me show you what I mean by that. It means if you feed in an image, lighting up all 784 neurons of the input layer according to the brightness of each pixel in the image, that pattern of activations causes some very specific pattern in the next layer, which causes some pattern in the one after it, which finally gives some pattern in the output layer. And the brightest neuron of that output layer is the network's choice, so to speak, for what digit this image represents. And before jumping into the math for how one layer influences the next, or how training works, let's just talk about why it's even reasonable to expect a layered structure like this to behave intelligently. What are we expecting here? What is the best hope for what those middle layers might be doing? Well, when you or I recognize digits, we piece together various components. A 9 has a loop up top and a line on the right. An 8 also has a loop up top, but it's paired with another loop down low. A 4 basically breaks down into 3 specific lines and things like that. Now in a perfect world, we might hope that each neuron in the second to last layer corresponds with one of these subcomponents. That anytime you feed in an image with, say, a loop up top, like a 9 or an 8, there's some specific neuron whose activation is going to be close to 1. And I don't mean this specific loop of pixels. The hope would be that any generally loopy pattern towards the top sets off this neuron. That way, going from the third layer to the last one just requires learning which combination of subcomponents corresponds to which digits. Of course, that just kicks the problem down the road, because how would you recognize these subcomponents or even learn what the right subcomponents should be? And I still haven't even talked about how one layer influences the next, but run with me on this one for a moment. Recognizing a loop can also break down into subproblems. One reasonable way to do this would be to first recognize the various little edges that make it up. Similarly, a long line, like the kind you might see in the digits 1 or 4 or 7, well, that's really just a long edge, or maybe you think of it as a certain pattern of several smaller edges. So maybe our hope is that each neuron in the second layer of the network corresponds with the various relevant little edges. Maybe when an image like this one comes in, it lights up all of the neurons associated with around 8 to 10 specific little edges, which in turn lights up the neurons associated with the upper loop and a long vertical line, and those light up the neuron associated with a 9. Whether or not this is what our final network actually does is another question, one that I'll come back to once we see how to train the network. But this is a hope that we might have, a sort of goal with the layered structure like this. Moreover, you can imagine how being able to detect edges and patterns like this would be really useful for other image recognition tasks. And even beyond image recognition, there are all sorts of intelligent things you might want to do that break down into layers of abstraction. Parsing speech, for example, involves taking raw audio and picking out distinct sounds, which combine to make certain syllables, which combine to form words, which combine to make up phrases and more abstract thoughts, etc. But getting back to how any of this actually works, picture yourself right now designing how exactly the activations in one layer might determine the activations in the next. The goal is to have some mechanism that could conceivably combine pixels into edges, or edges into patterns, or patterns into digits. And to zoom in on one very specific example, let's say the hope is for one particular neuron in the second layer to pick up on whether or not the image has an edge in this region here. The question at hand is, what parameters should the network have? What dials and knobs should you be able to tweak so that it's expressive enough to potentially capture this pattern, or any other pixel pattern, or the pattern that several edges can make a loop, and other such things? Well, what we'll do is assign a weight to each one of the connections between our neuron and the neurons from the first layer. These weights are just numbers. Then, take all of those activations from the first layer and compute their weighted sum according to these weights. I find it helpful to think of these weights as being organized into a little grid of their own, and I'm going to use green pixels to indicate positive weights and red pixels to indicate negative weights, where the brightness of that pixel is some loose depiction of the weight's value. Now, if we made the weights associated with almost all of the pixels 0, except for some positive weights in this region that we care about, then taking the weighted sum of all the pixel values really just amounts to adding up the values of the pixel just in the region that we care about. And if you really wanted to pick up on whether there's an edge here, what you might do is have some negative weights associated with the surrounding pixels. Then the sum is largest when those middle pixels are bright, but the surrounding pixels are darker. When you compute a weighted sum like this, you might come out with any number, but for this network, what we want is for activations to be some value between 0 and 1. So a common thing to do is to pump this weighted sum into some function that squishes the real number line into the range between 0 and 1. And a common function that does this is called the sigmoid function, also known as a logistic curve. Basically, very negative inputs end up close to 0, very positive inputs end up close to 1, and it just steadily increases around the input 0. So the activation of the neuron here is basically a measure of how positive the relevant weighted sum is. But maybe it's not that you want the neuron to light up when the weighted sum is bigger than 0. Maybe you only want it to be active when the sum is bigger than, say, 10. That is, you want some bias for it to be inactive. What we'll do then is just add in some other number, like -10, to this weighted sum before plugging it through the sigmoid squishification function. That additional number is called the bias. So the weights tell you what pixel pattern this neuron in the second layer is picking up on, and the bias tells you how high the weighted sum needs to be before the neuron starts getting meaningfully active. And that is just one neuron. Every other neuron in this layer is going to be connected to all 784 pixel neurons from the first layer. And each one of those 784 connections has its own weight associated with it. Also, each one has some bias, some other number that you add on to the weighted sum before squishing it with the sigmoid. And that's a lot to think about. With this hidden layer of 16 neurons, that's a total of 784 times 16 weights, along with 16 biases. And all of that is just the connections from the first layer to the second. The connections between the other layers also have a bunch of weights and biases associated with them. All said and done, this network has almost exactly 13,000 total weights and biases, 13,000 knobs and dials that can be tweaked and turned to make this network behave in different ways. So when we talk about learning, what that's referring to is getting the computer to find a valid setting for all of these many numbers so that it'll actually solve the problem at hand. One thought experiment that is at once fun and kind of horrifying is to imagine sitting down and setting all of these weights and biases by hand, purposefully tweaking the numbers so that the second layer picks up on edges, the third layer picks up on patterns, etc. I personally find this satisfying rather than just treating the network as a total black box, because when the network doesn't perform the way you anticipate, if you've built up a little bit of a relationship with what those weights and biases actually mean, you have a starting place for experimenting with how to change the structure to improve. Or when the network does work, but not for the reasons you might expect, digging into what the weights and biases are doing is a good way to challenge your assumptions and really expose the full space of possible solutions. By the way, the actual function here is a little cumbersome to write down, don't you think? So let me show you a more notationally compact way that these connections are represented. This is how you'd see it if you choose to read up more about neural networks. Organize all of the activations from one layer into a column as a vector. Then organize all of the weights as a matrix, where each row of that matrix corresponds to the connections between one layer and a particular neuron in the next layer. What that means is that taking the weight...
Okay, I think I should stop here because they talk about the linear algebra. Whenever you're in the second year in your college, you should learn, if you're a STEM student, you should learn this linear algebra. But in the next year, you probably can take this artificial intelligence course, class. Right? So, okay, so yeah, I really like this video. So that's why I want to introduce to you guys. In our slides, you should have access to it. Yeah, so it's right over here. This PPT slides is available in the master document. You have access to it. You can watch this video again. It doesn't take a long time. The useful part is about, I think it's about like 20 minutes for the whole video. If you just want to cut in the halfway, it's about like 15 minutes, right? So good. So do you like it? You give me a response. You give me a response and say yes or no. Maybe no, but I think for majority of them, you should like it. Oh, can you follow it? Let me ask you this way: can you follow? Kind of. Okay, great. Okay, I think you guys are kind of positive. I'm very glad because I know you guys are very smart guys. Smart is not. Is that really important? Yes, kind of. Smart is important, right? But the most important thing is you're going to try different ways and put your effort, try different ways. That is the way that you can learn well, okay? Yeah, Daniel, it is a little bit, it looks like let's say this way, it is not easy, but it's complicated because it has so many simple nodes. When we put them together, the computation, effort is huge, right? Yeah, especially as it says, we have like thousands of those parameters to tune in order to make a good artificial intelligence model, right? Because we're gonna find all the weights and the bias, that kind of thing, in order to make a good thing, right? Good model. So that's true. That's why we need very high computational capacity, like a really modern computer with GPU. Have you heard about the GPU? GPU is graphic process unit, which means it can handle data very well. It's better than CPU that in our average PC. Okay, so, but anyway, you're gonna get there. Daniel, you're still in elementary school, so absolutely, it is way beyond your age. Usually, this kind of, let me tell you one thing. When I touched this, I was in the I took neural network class when I was a master student. When I was a graduate student, yeah. So, and this is my kind of like related to my research area when I was a PhD, right? So this is fairly advanced. That's true. If you can kind of, right, understand the concept, that would be good enough. Why? Because, yeah, guess what? I should make this clear. All these are just for your information. All our projects has nothing to do, well, we don't actually use these formulas or whatever. Okay, we don't use this. Remember, we did that. We used the personal image classifier and the peekaboo thing, right? In the previous two classes. Well, those are trained by this kind of thing, the neural networks, but we just use it. Okay, we know how to train it, but what's inside? This is I try to explain what's inside. You don't have to understand this. However, it is good to have a concept so that whenever you do training, you kind of feel you have a direction, direction to go. You feel like you are not lost, right? You feel like you have a direction because you can imagine what's happening within the black box. This is really a black box. Okay, it's very complicated computation inside. But anyway, you're still gonna feel something, some operations in the, a black box. That's the purpose. I'm not saying you're gonna understand all these and our programming gonna based on this. No, our programming will not based on this. Even though you are at your college level and a graduate student level, you still don't actually touch these mathematics. Why? Because the open source has everything. Remember last time I showed you guys the TensorFlow code. That's only, maybe a dozen lines of code. That's all you need. And everything is inside. Someone has already done it. And so one guy has done this, and you go, and all we can use it, right? But we know how it worked inside. That's the idea. Okay. Yeah, I think it's a good time to have a break. Let's have a 5-minute break. We'll come back in 5 minutes. At the same time, if you have question, yeah, just before we have a break, do you have some quick question? Let me see. I don't see any. Okay. I will be here. If you have question, you can all the time. You can type it in the chat. Okay. And now let's have 5 minutes break. Okay, are you guys coming back? Wonderful. Okay, yeah, let's restart. Now we're gonna do, what we're gonna do? We're gonna do our project with the MIT App Inventor. What we're gonna do is today is there is something very interesting, right? So have you heard about the Instagram or the Snapchat, right? So you actually can mask your face. Take this example. So there is a girl, right? And she can put some like air and whisker, put on his face, on her face. Well, the interesting thing is when she moves, right? She can move around, and she could be closer or maybe further to the camera, right? So this two ears and the whisker should be changed the position and the size accordingly. Okay, so this part we have to have, artificial intelligence. So this is what we have. Okay, we call it the face mesh. What does that mean? The face mesh means the artificial intelligence can see there is a mesh on our face, and the artificial intelligence gonna figure out each point in that on our face. For example, the artificial intelligence, gonna put a mesh on our face, identify each locations, right? If you look at here, this is a left forehead, right forehead, right eyeball, eye top, inner corner, eye bottom, cheek, mouth top, mouth bottom, all kind of things, all the points. There's many points. I think there is I can't remember how many points. It's about maybe 200 points on your face. Yeah. So whenever you move, those 200, 184 maybe. Yeah, I gotta check. Okay. So those many points, it's gonna dynamically track the points on your face. Okay. So this is called this model. Okay. This model is called the face mesh. This face mesh model is essentially created, I believe it's created by Google. Okay, it's created by Google. So, but anyway, it's invented by Google. The implementation, there is many implementations, right? Anyone can implement it, can program it, make it happen. So, but this is the face mesh model I want to mention. Well, according to our, this is our cell phone, right? Our cell phone. So this MIT App Inventor, they actually they provide two sets of pictures. One is for the cat, right? This is for cat. This is for lion. Yeah, the animal, right? The king of the animal. Yeah. So it's essentially got the two sets of pictures in our MIT App Inventor. What we do is, so the idea is we want to place this ears and the whisker in the appropriate place, right? What is the appropriate place? Well, there is two things. If you look at here, this width, the width is the width of the face. How wide is the face, right? So this is what we want to check. And what is the whiskered height, right? Height is between, if we look at here, it says between eye and the mouth. Okay, so somewhere. Okay, so here is, how about the ear? The ear is nose and the cheek, right? So we're gonna, so this is the idea. So when we implement it, we're gonna see how to do it. All right. So the face mesh application can detect the head movements when you move around, right? Can detect the movement in camera and the calculation of facial feature points and update it over time. Yeah, of course, right? So when you move, your mesh will move. kind of move. All the points, the coordinates of each point is going to change, right? So yeah, that's what it says. We're going to do this. That will be very interesting. And also, let me tell you, as I just mentioned at the beginning of this class, that this same thing, Kevin created a project using this technology, right? Created a application, a project for science fair, International Science and Engineering Fair, and he wants the third grand prize. I'll show you the details about that, the video and the report, technical report, so you get all the details. Okay. Right. All right. So let's say this way. Let's say what we're gonna do. These are provided. These are preset. We don't set it. MIT App Inventor set it already for us. What it does is, essentially in the screen, we have a canvas, right? A canvas, we can put like different colors and images on that. So we're gonna place a, what is this? This is a image, right? Image spread, yeah. Put an air, a left air, right air, and a whisker on top of this canvas. Yeah, and also we have two buttons. What is that? Take photo. Yeah, take a picture and share your pictures, right? So these two buttons, and yeah, and yeah, we have some like invisible, non-visible components, which is the web viewer. Why we want a web viewer? Because the web viewer is used for the camera, right? The camera. Even in the previous two projects, we did this. We used this web viewer. And what about sharing? Well, sharing, this is the first time we use sharing, but sharing has nothing to do with our, artificial intelligence. It's just a new component that we can use. Sharing essentially is a component that can find all the shareable applications on your cell phone, okay, and then list them and ask you and give you a prompt, a message, and ask you which one you want to post to. For example, you have Facebook, you have, Instagram, and you have Google Drive. So you can select one of them and share and upload to whatever you want to, the application that you want to share with, right? So that's it. This is the front end. And also, if you look at this pink stuff, I don't know. I think, this pink stuff is the extension. It's the face extension. What is the face extension? It's essentially the model, right? The model. Yeah, the model. We can download from the MIT extension page. Remember, I gave you twice already in the previous two courses, and you can download it. But in our class, the AIA that I have already imported already. So you can either download yourself or you can use mine. Okay, so this is the front. Yeah, this is the front page. This is the user interface, right? So, all right, yeah. So what I want to do from here, let me see. Okay, so I just want to, let's do this. As long as we understand the front end design, this GUI, this user interface design, let's go to the MIT App Inventor. We can do everything over there. Okay, that would be the best. That is the best way that we practice. Okay, from here. Let me type MIT App Inventor, AI. Open this page. This page is all about the AI, right? We're gonna scroll down to the to this, the second last one. Look at here. This is the last one. This I want to open the second last project. Okay. Yeah. Let me click on that. Okay, so it is here. But anyway, yeah, we're gonna click on this URL. This URL gonna lead us to a project page. Okay, so MIT project page is very good. Why? Because look at here. This is where you can do your coding, right? You can do your programming. However, on the left hand side, there is it's called a slide bar, right? This is a left slide bar. You have a tutorial. You can follow whatever on the left and implement in your MIT App Inventor. So this is really good stuff. Let me amplify a little bit. If you have questions, you can always, let me know. So what I want to say is, look at here. This is exactly how we described, right? We have a canvas, this much, and we have left ear, right ear, and whisker. 3 pictures. We just place it over here. So essentially, I put the line here. If you want to change to some other cat stuff, of course you can change, right? Oh, I think I did it right. I did it wrong. I put the cat whiskered. Yeah, but this is like a funny. But anyway, you can put the either cat side, or you can put the line set. Okay, let's change this. Let's change this to to the cat set. So this is a cat stuff. Okay, so yeah, that's it, right? And underneath we have sharing. That's a function. It's actually nothing to do with AI stuff. It is just a share. You want to take a picture and upload to somewhere and post it somewhere. You can do it with the sharing. Yeah, but it's a good thing to know, right? And also this is important because this is the face. It's called a face extension, right? Face mesh extension. So the face mesh extension is actually here already. It's already imported. Actually, you should download in the download page. I'm not going to repeat that because I did it twice. Okay, if you don't know, let me know. I'll tell you how. Or any other students can tell you how. Okay, so you can actually import it from. You can download it and import it. Okay, so put it here. Okay, any questions so far? Any questions? If you want me to, slow down or stop and repeat something, let me know. Okay, so there is a text-to-speech. I believe you are very familiar with the text-to-speech, right? Yeah. So you guys should be fine with text-to-speech. So that's all about the front end. Okay. So let's go to the back end. Let's go to the back end. Okay. Well, actually, guess what? This MIT App Inventor has already implemented the majority of the things. Okay. So they have the code already. So we just need to add a little on them. But anyway, let's follow this tutorial. Okay, this tutorial. Again, usually you don't worry about the setup of your computer. Your computer has already been set up. You're done with this. Okay, so just go to the project. Face mesh filter camera. Okay, so there's 17 pages. Look at here, 17 pages. This is the first one. So it's going to talk about the introduction. We don't worry about that because I've already introduced. The next one is, the face mesh model. It says it's created by Google, I believe. Does it say? Okay, but anyway, so this model is an external model, right? So we have a face extension, this pink stuff. So we need to download it. And actually, I've already done this. Okay, don't worry about that. Yeah. The third one is the GUI, the user interface. The user interface is exactly what I explained to you. I've already explained to you. So we don't worry about that. Okay, so yeah, we have already done this. And also, okay, so this face mesh model gonna create what? A mesh, a face mesh, right? A face mesh is actually like this, right? With all the points, even though some points without the name, well, actually all these points have names, okay? So some important points are labeled with some like explanation, but all of them, if you want, you can label all of them. And actually they have, if they don't have all, they have majority of them labeled, okay? So that's the face mesh. The next one, okay. So how if we know the location, let's say we know the forehead, this is a forehead, right? If we know the forehead, that point, what we expect to get, we get two numbers, okay? A list of two numbers. One is the X, one is the Y, just two numerical numbers, okay? So there is a list of these points, and in the list, each item in the list is just two numbers, is a list of numbers, okay? So that's it. And well, how that two numbers can be used? Well, essentially, we should know this. And actually, we mentioned this in the 203. If you're not there, I just mention it again. So the origin point is over here, not like our mathematics. You guys probably know mathematics. In our mathematics, the origin is usually the left bottom. The left bottom point is the origin, right? And vertically up is the y-axis, and horizontally, right is the x. So this is our coordinates in our mathematics for some reason. Okay, for some reason. The designer of our cell phone, they use another coordinates system. What is that? Their origin is at the top left. Okay, so this is from 0 to 300. The y-axis is actually point down. Okay, so this is 0, and the 200 on y is here. It's at the bottom, right? So we're gonna notice this. Okay, so this is what we need to know about the difference between our math at school and the actual coordinates in the on the screen. Okay, I don't know who did this. Probably he's not educated. Okay, but anyway, so the next one is, yeah, we have 6 pictures. If you look at these pictures, it's actually, the 6 pictures are, either a set of cat, a set of full line, right? For each of the animals, we have left ear, right ear, and whisker. Yeah, whiskers. Okay, so, all right, so the next one. Okay, so yeah, we can choose either of them. It doesn't matter. I just show you how we can switch. You can select anyone. Okay, so yeah. So once you finish, you should see something like this. Yes, we did that. Why? Because yeah, we show this, right? This is the one. We have this already. Okay, it looks like we are half done. We're half done. Now, we have some code. They say preliminary code, which means they're there already, or we don't have to take it. What it says, we have like a take photo button. Remember that? There is a button over here, take photo. Yeah, take photo button. That means you can take a photo and save it, and you can share it, right? Look at here. This is not our emphasis. This is just a function in the application, right? It's not about AI. This is just take a picture. When you take a picture, you know, so we're gonna save the, yeah, we're gonna save that picture to what? To the, we're gonna save the picture on the canvas, save to a file. The file name is character camera, and get the count. The count is, this count is always increasing. Okay, whenever you take one picture, the count is increased so that there is no two pictures have the same count number. That way, the file name will be distinguished, will be unique, right? Will be distinct, will be unique. So that means we don't confuse with two pictures, right? Yeah, you got this, right? Yeah, I know you got this. And then you speak it out. Just say it. Text to speech dot speak. You can say it. Yeah, photo capture, just like that. All right. So this is what we're gonna do. This is in the preliminary GUI code, which means it has been provided already. Okay. So yeah. Before we do this block, we actually set two global variables. One is the photo count. The photo count start with 1, and this can be increased. Remember the block here? Yeah, we increased it because whenever we take one, it's being used. That number is being used. We're gonna create a new one. And also, we wanna take a most recent photo. I think this is a string, which means this is a kind of like a file name, right? Yeah, this is a string. We can put a file name, save file name in it. Okay, and also, yeah, share photo button. When you click the share button, look at here, you have a share button, right? Right over here. Yeah, whenever this is being pressed, so we essentially just share it. Yeah, sharing one dot share file. Just give that most recent photo file, the file name. Just get that photo file and share it, right? So okay, this is really just want to explain to you because it's been there already. Okay, we don't program it. MIT App Event has already put that part, okay, because these part are non-AI. These are some like other function. So, all right, yeah, there is some like a helper function. Help. Well, I think there is a function which is the okay, so how can we place an image? Let's say we have a left ear, right ear, and the whisker, right? Whisker over here. So how can we place it? It's essentially we're gonna place some location. We're gonna put it in some location. Put the image, right? Put the image. Given the face point, let's say we want to say this is my left forehead. I'm going to use this left. I don't know which one is that. Okay, so it depends on how you look at it. This is my left forehead. It's right over here. I want to place my ear centered by this point. So we're going to use this formula, right? Well, essentially what this says is this is the point, you know. So we're going to see the mathematics. We just identified it, but what we want to know is the face point, whichever face point you want to say ear, okay, mouse, nose, whatever. You're given the face point, you want to place this image on that. Either it is a, left ear or right ear, or, yeah. So this is the function. We can place the image at the location that we want. But for now, the mathematics is not there. Okay, we're gonna figure out based on the situation, which means which one you want to place. That depends, right? But we're gonna have some mathematics over here. You probably want to see here. So what we want to do is, this is what we want to do. If we know, if we know this point, that means the image, well, guess what? The image, we're going to place it over here. Okay, the image, we're going to place it here. How can I calculate it? This is the forehead, right? This point, oops. Yeah, this point is actually the forehead. Given this forehead, and we know the width, right? So we actually want to calculate the point on here. This is the image, because if you have an image, you say, hey, I want to place it here. That means you place your image like this. Okay, so this is the thing that you want to identify about your image. Okay, so this is a calculation. There is some like mathematics. You're going to figure it out. Okay, so this is not hard. Why? Because if you have this and we have like a half of the height and half of the, the width, and we can calculate this XC and YC. Okay, so no big deal for you guys. I know you should be able to do that. Okay, so this is how we place a image, right? This function. Now, let's go to the next one. We're kind of like a 2/3. All right, so what we want is essentially, remember we visit this place image already, right? But we want to do the calculation. Let's say this way, if we have a face point, we actually, based on the previous analysis, right? So we can come up with this formula. We just do this formula. We just do this formula, right? Yeah. Why we do this formula? Let's go back a little bit. One more. Yeah. So this is the formula, right? Look, these are the formulas. Okay. So these are the formula to calculate the XC and the YC. With this one, we actually can go to the next page. Go to the next page. Yeah, so this is the formula. This is the implementation of the formula. So if you can just do it, yeah, you just implement it. There is like instructions over here. It's really great that you can learn a lot. And all these are very important whenever just one day you want to move it to the text-based coding. It's also very, very useful in doing that. Okay. All right. So the next one, face update. So, oops. Yeah, the face update. So the face update is, well, essentially when the face extension detect the face is moving, right? Face update. When you move, the AI is gonna detect it and recalculate your mesh. Okay, so what you're gonna do is you should move the air and the whiskers, right? Accordingly. How to move? You're gonna do two things. Number one, the location move, right? Location, you're gonna move your location. Number two, you're gonna resize it. Resize. What does that mean? Because when I close or when I be further to the camera, the size of my head is different. So your ear and the whiskers should be differently. So from here, I just want to say, we have two functions to create. One is moving, one is resizing. It's not implemented. We're going to implement it. Okay, we are going to implement. Okay, but this is the skeleton. This is the function name over here. Okay, let's go there. How can we create the moving? Let's do this. The moving is okay. So the moving, based on the moving, it's very straightforward. What? Okay, so the moving means you're gonna place the image in the new place, right? It's always the left ear. The image of left ear should be, placed in the left forehead, right? It's always like that. Okay, why? Because we did that in the place image. Remember that? The place image is the function that we implemented. Yeah, so we just call that image. Why? Because given this forehead, there is a formula we can calculate where the image should be located, right? The XC and the YC, remember that? So we just call those functions. We just say, hey, left ear, right ear, and the whisker should be on just based on left forehead, right forehead, and the mouth top. Okay, so this is a moving, right? This is a moving. Yeah, well, actually, so we have a resizing part. We have a resizing part. The resizing is essentially, let's do this. Okay, the width is, well, essentially, your whiskered width should be accordingly to the face width in the artificial intelligence, right? You just adjust it accordingly. Look at here, whiskered width, whiskered height, whiskered left ear width, left ear height, and about the right ear. So you're gonna adjust it. Why? Because you just measure. You just do the same thing. You detect from the artificial intelligence. The artificial intelligence, the face mesh, gonna tell you those numbers, and you just put it in the picture, resize the picture. That's it. Agree? So yeah, essentially gonna do something like this. I'm not gonna explain this. I think we did this before. So, but the code is, yeah, just detect it and set the image size accordingly. All right. Okay, so what else? That's it. That's it. With all this down, we're gonna test our applications. Let's do that. Okay, so let's do that. When we finish, we're finished. How can we do that? Let me do that on my machine. Okay. Okay, so I want to set the air droid. Come on. Yeah, okay, so it's over here. Remind me later. So what I want to do is I want to connect. Yeah, I want to. Okay, so I want to connect my mobile device to my PC, right? So I'm trying to do this and connecting. Refuse, request for casting, allow, right? I allow, so it's connected, it's connecting. Okay, I want to start now. So it is sharing, right? Okay, great. So now you see my mobile device, right? So essentially, I want to open this MIT App Inventor, and I want to see here. I scan it. It's still compiling. Oh, wait, where's my mobile phone? I'm trying to. Okay. Am I sharing my mobile device?
No, because I think you hid it.
I what? Oh, it's hidden? How can I make it hide?
It's on the side of your screen.
Oh, it's right over here. How can I drag it out? Strange.
Drag the top bit.
It's here? Yeah. Oh, yeah. Okay. Let me because that's right. You're right. Let me open it. Oh, here it is. Look at here. When I move around, right? Yeah. So you're gonna see the air and the airs and the whisker gonna move, and also the size will be, changed based on how large is my head. So that means this artificial intelligence can correctly create a mesh, right, dynamically. So this is the application. All right. So yeah, you can see that, and I will post this solution to you, and you guys gonna build your own stuff, just like what I did. Okay. So essentially, everything is here already. Is on the left-hand side tutorial. You just want to follow the instruction. So my code is right over here. I will send this to you as well. It's not a whole lot of code. It's just this much, This is everything. Yeah, this is everything. Okay, so that's good. Yeah, this is the third artificial intelligence model that we have learned, and this artificial intelligence model is really, really useful. So I'm going to introduce. Let's go to our slides. Okay, so yeah, we covered all these. Okay, now, so yeah, I want to talk about our homework. Okay, the homework, essentially, you're gonna do the same thing. However, do some additional stuff for me. If you look at here, this is the cat and the line, right? So now I hard code the selection over there. Can you make it selectable by user? Yeah, you can put a button and say, yeah, I want to select this set or that set. Based on your selection, you can select it dynamically. Rather than now, I just put it, remember, I just currently, I simply set it here. Look at here. I just gave the picture's name, right? So if you can create a button, you can switch from one to another. That is the homework. Okay, so you extend it. That's number one. That's the first thing I want you to do. And I want you to do the second thing is, well, essentially, if you look at this face, right? This face was a mesh. Why? Because this model can put the mesh on your face, which means where are those points? So the mesh. You try to push the mesh that can see how good this application can track your, the points on your face, right? So how to do that? It's very, very easy. Look at here. If you click on the face extension, there is a place you can check show mesh. Okay. And if you uncheck it, there is no mesh on your face. So just want to, you just test this kind of thing, right? The number one, number three. And the number two is, I think it's optional if you want to do that. What this says is, look at here, this girl, when she opened the mouth, right? What's happening? Because the upper mouth point and the lower part, the bottom mouth point, the distance will be large. Okay, if he close his mouth, that distance will be very close, right? Based on this, you can detect the distance between the upper mouth and the lower mouth, and you decide whether this girl is open mouth or closed mouth. And you put some, what you guys call this? This little face. What is the name for you? Can you tell me how you called it? Can you type it? It's called an it's how to pronounce it. Emoji, right? Yeah, the emoji. Yeah, just put some emoji over there if you can find it. Yeah, that's the homework. So if you have this, you can just do the same thing as I do. Just put a little bit more things on that as your homework. Yeah. So this is your homework. Okay. So besides your homework, I really want to introduce some additional stuff for you. So for this application, you probably gonna think, yeah, this is a homework, but actually, Kevin Ming just used this project, did a very good project which won the, a grand prize in the science fair, International Science and Engineering Fair. What he did is he used the face mesh, right? Locate some points. Well, essentially, he used another model, not this model, to see where the rotation, the angle, the angle of my head, based on this, based on the movement of the angle, he want to detect whether I'm focused on driving or not. Whether I just chat with people, whether I feel like a sleepy or something, right? This is a project inspired by an accident from his friend. His friend Jonathan got hit by the car. His best friend got hit, and he said, "Oh, I mean, the driver was very sad." He said, "Oh my." I was not intentionally do this, but I was not focused. He's distracted. He was distracted, and this can detect whether the driver got distracted. If you look at here, the picture on here, this is a camera. This is a camera facing the driver, and this is a camera facing the road, which track whether keep your route along the line, right? And also, if you look at here, he put a mobile phone to see whether the rotation. This rotation gonna tell the data gonna tell the model whether you are turning, right? Because the turning, well, usually if you drive straightly, usually that's less risky. The most risky situation is when you turn your lane or turn the direction. So this is gonna tell you whether you are about to do an risky operation. Okay, so this is called the onboard diagnosis tool, which means this is the plug-in. You can collect all the engine speed, that kind of information. Let me see whether. Yeah, we can take a look at the OBD2. So yeah, essentially OBD2 is just a little device you can purchase from Amazon for about like some $30. There is a way you can plug into your car so that you can collect the, yeah, let's take a look. I think what it says is you can plug into a place, let me see, in the car. Maybe it's here. Yeah, there is a plug-in. You just plug it. You get all the data from your car. Remember when you have a vehicle inspection? Your parents gonna bring you to the vehicle inspection. The guy gonna plug in some meter and check it, right? Check your status, right? Check the emission, that kind of thing. Check status. That's essentially they have a OBD2 plug into your car. And actually the plug, he purchased the Bluetooth OBD2 and plugged it in so that we can collect all the information about this vehicle. Okay, so with this kind of information, we can do some artificial intelligence, machine learning, and learn when it will be a dangerous, a risky situation, so that whenever it's risky, we're gonna alert you. Well, you can do something, right? If you are a vehicle automotive, if you are a vehicle manufacturer, you can apply this technology and put some some protection, safety equipment, safety system on it. Okay, so if you guys want to ask what I can do after learning this artificial intelligence, let me tell you, there is a whole lot of ways you can use it. You can use it in hackathon, right, which is the programming competition. You can also use it in science fair. You actually can do programming projects in all subjects. For example, like mathematics, physics, chemistry, biology, engineering, right, electronics, software, and even the robotics and intelligent machines. That's a category in the science fair and science and engineering fair. So yeah, you can do a lot of things. A lot of students think, they say, oh yeah, I want to do biology. No, if you go biology, you can still purely using your computer programming skills to do all subjects. Essentially, there is no limit. Yeah. Okay, so for this one, this is a project in the robotics and intelligent machine category. Okay, so let me put an interview, TV interview video. This video is actually, it's like 1 minute or two, maybe 2 minutes, very short. And if you want to see the presentation, I will be here. There is a long video. I don't think I have time to play it in class. However, if you want to see the report, you say, hey, give me some details, right? So you can click on this, the last one. This is an IEEE place that this is the whole thing that this is the whole thing about this report, this paper. It's actually a paper. I think there is if you're really interested in the details, I think when you log into this place, you will have to purchase. You're probably gonna, oh my God. Okay, you're probably gonna pay some money If you're interested in the free copy, just let me know. I'll send you a free copy. You don't pay. Don't pay. Okay, let me see whether we do have one PDF available online. PDF. Okay, so there is a PDF over here. No, it's not ours. This is from someone else. Yeah, this is our paper, right? I'm not sure, but anyway, I can ask Kevin to provide a free copy to you guys if you want. Oh, maybe this is the one. No, this is another one. But anyway, so yeah, we should have a paper. You guys should have a paper. Right. If you don't have it, let me know. Oh, but anyway, let me play a video which is very short. It's a description, so that I hope this can encourage you guys to do science fair projects using this kind of like using the projects we learned from artificial intelligence. And this is one of the projects I want to introduce. And the next time I will introduce you three three projects which won the top awards in prestige competition. Okay, so this is the first of them, and all the projects are coming from what we did what we're doing in our class. Okay, so this is the link I want to check with you. This is a very short link, a short video. Yeah, unfortunately, we have to, this is an advertisement. Why? Because we have to publish it in China. In the United States, it's not acceptable because of the copyright, right? So yeah, that's why you see this is in some Chinese website.
Applied to traditional ADAS systems, I could save about 8,000 lives a year. High School of Plano, Texas. Hi, my name is Kevin. I'm a 10th grader from Jasper High School of Plano, Texas. So I built a vehicle action prediction system with artificial intelligence that can essentially anticipate drivers' turns and lane changes before they actually make them. So kind of the impetus behind this project is that a lot of cars are now coming out with advanced driver assistance systems, lane departure warning, forward collision warning. But the problem with these is that they're reactive. So by the time that they give you the beep, the warning that there's a car coming up at you and you need to get out of this disaster, it's often too late and we're not given enough time to react. So the purpose of my project was to improve this into a proactive system where the driver would be warned before he makes that decision that would get him in trouble. There are three types of important information. First, what the driver is doing, the driver behavior. Second, the vehicle dynamics, what the vehicle is doing. And third, how the driver is interacting with the vehicle, what kind of inputs he's giving it. So essentially, I use this that demarcates 68 landmark points on the driver's face. And then from this, I can extract the 3D position in space and extract things like the Euler angles and the angular rotation. And I used a classification and regression tree to select the most important features to get rid of the noise, and so that eventually achieved a better fit with a recurrent neural net. So finally, using all the clean, filtered, and labeled data, I used a recurrent neural network with long short-term memory to essentially model the driver's patterns and map these to predictions as to what they're going to be doing at the end of the sequence. If this were applied to traditional ADAS systems, I could save about 8,000 lives a year.
Okay. So this is the project. I hope that can inspire us to continue on. Yeah. So that's pretty much all we have today. Okay. So yeah, you got a violin lesson. Yes, please go ahead, and we're done with this one. And any quick questions before we close this? Okay. Yeah. Okay, Marco. Yeah, that's okay. Yeah, if you don't have question, we can finish here. Just wait a second. So how can I set up a office hour for you guys? Okay? So if you guys can send me, are you guys in the Discord chat? I mean, Discord group? Okay. So if you're in the Discord group, I hope I can invite you to this Australia Sydney group. I need to know your name so that I can invite you. Okay, can you do this? Can you guys do this? You connected to me. My name is there. You connect to me and tell me who am I, because you guys using all kinds of names that I do not necessarily recognize, right? You connect to me, make a friend with me so that I know who you are. And then I can bring you guys to the Cine group that we can discuss a time that I can give you office hour. I'm not comfortable if you don't have office hour. I'm not sure how is your homework going. So I need to know that. But anyway, trying to connect to me. Okay, make me a friend in your, in the Discord. Remember that. Okay, I give you 24 hours to do this. All right, and then I invite you to the Cine group, and then we can discuss over there. Otherwise, in other places, there is a lot of noises. Okay, that's all I have. You guys have a good day, and yeah, have fun with this artificial intelligence. All right, goodbye. Yeah, bye-bye.